Okay, so logarithms related to exponential functions. All right, that's what we're going to take a look at. We are actually going to do something in Desmos kind of to introduce this idea, and then I was kind of debating, but I think I'm going to do it anyway because it's kind of neat. There's a little video, if I can find it, of a guy, a science guy, and he does a cool thing with what is an application of a logarithm. We can talk about that a little bit so you can kind of see where that is, and then we'll kind of see where we're at with that before we break into 4.5, which is properties of logarithms. Okay, and then there'll be quite a few examples of stuff. All right, so let's do that. So what we're going to do is go into Desmos here, and I want to show you what a logarithm is and how it's related to an exponential. So I'll give you a couple minutes here to get into it. Also, don't forget, if you want to check your grade or update it, I can download the Excel spreadsheet for you at any time, and we can look at that. All right, so we're going to open up a table. So I'm going to click on here, go to table. All right, and I'm going to type some numbers in here, starting with 0. Not 1, that's just my cable getting in the way. I'm trying here. Get over here. Okay, so we're going to start with 0, and we're going to go 0.1, and then see how it figures out what you want. Isn't that nice? Just hit enter, and it figures it out. We're just going to go all the way down to 1. Okay? So we went 0, 0.1, and hit enter, hit enter, hit enter, and figured out that I wanted those numbers for me all the way down to 1. All right? Now, up here on the top, we're going to enter an exponential equation. So I'm just going to click up here on the top, backspace that out, and go 10 to the, so I'm going to have to go get that down here. I think I'll use this. And then x1. So it understands that what we're going to do is put in these values into this equation. All right, so we have x1, 10 to the x1 here. All right, which gives me this nice graph. All right, nothing too exciting, it's just an exponential. Okay, now I'm going to come down to this second line down here, okay, and I'm going to add another table. Now, I played with this earlier. I wish there was a way to do this differently, but there is not. Okay, so what we want to do is, when we we're going to flip these two things around. All right, so these numbers I'm going to put in here, and I can't copy and paste them because it doesn't let me do that. All right, so what I have to do is just type them in. Now, I'm not going to type in to, what is that, 6, 7 digits or something like that. I'm just going to go ahead and put in first couple. So I'll go 1 there, and then I think it was 1.2. See, it just doesn't quite make it. There we go. Come on, 1.25. Okay, and then this one is 1.58. And then I have to scooch back up to get, I'm just going to put 2 in for this one because it's really close. And 2.51 for this one. .16. And then here, I just do that same thing that I did before, but it won't go. It doesn't understand what you want on this side. So you gotta actually type those in. There. So those are the numbers that we want right there. I'm going to change this to a different color. There we go. Okay, so here's my green ones, here's my blue ones, all right? And now I'm going to do this, and this is going to give everything away. Okay, how's the blue and the green related? They're inverses, okay? Because remember that in an inverse, two things happen. Okay, what happens to the domain and range? They flip, right? And the graph of a function, the inverse and the graph of the function here, so the green and the blue, how are those graphs related? And there's a reflection over the y equals x line, okay? So the blue is a reflection of the green, all right? Right over this line, okay? So they're inverses. So what does that mean? Well, that means that this, remember, was an exponential, okay? This is a logarithmic, all right? So the log is the inverse of an exponential. That's what it is. So like an exponential, which grows quickly here, so it's growing, right? Logs don't. It starts out pretty good, but then it just flattens out, right? Slightly grows. So it's just the inverse of it. Okay? Grows fast, grows slow, very slow. All right? So that's what a log is. So a log is an inverse of an exponential. Now, there's something that's really important when we're doing logarithms, and that's the definition of a logarithm, and it comes from this idea of it being an inverse of an exponential. So if I go, say, y equals 10 to the x, then that can be written as the log, and remember, the domain and range switch. So then this goes here, that becomes the input, and this x becomes the output. And you say, well, what happened to the 10? Well, the 10 is right there, okay? So if we have y equals, say, b to the x, then the log of y base b is equal to x. All right, that's the definition of a logarithm. So you're going to use that a lot when you're solving these little exercises on your assignment and on your tests and quizzes, whatever you're going to do. So you're going to use this a lot because it just comes up. So if you can actually do probably almost every single logarithmic problem if you can use the definition, okay? I mean, that's how it works. So for example, let's take a look at this. So if we have, let's take a simple one. So if we have 10 to the third, we know that's equal to 1,000, right? Written as a logarithm, that would be log, and the base is 10. There's your base, and the x's and y's are going to switch. So it's going to be 1,000 here is equal to 3. Okay? So this is the base. That goes there and there, the light blue. Okay? 3 is the power, so that was the input. Now that becomes the output. 1,000 was the output, but now that becomes the input. All right, so you're putting that into the log function. If we have 10 to the 5th, 1, 2, 3, 4, 5, then that would be the log base 10. There's our base of this number is equal to 5. Okay. Now logs can be any base. All right. When it's a base 10, that's called a common logarithm. All right. So I don't know if they mention that very much. So a common log has a base 10. All right. And that's because that's what everything was based on, right? Our counting system is all base 10. So that's why it's called a common log. But we could have, say, 2 to the 3rd is equal to 8. All right, so that means that the log, what would the base be? 2 of, what are we going to take the log of? 8, and that's going to be 3. Okay? The base is right here. That's your base. And logs can be any base. They can't be a negative base, I guess, but they can be any positive number. All right. So that's the definition of a logarithm. All right, and that's just, if you know that, you're going to be in good shape. What if you want to find the log of a number? So let's say you want to find the log of, we'll just go base 10 here. If it's a base 10, you don't even have to write it, but I'll just put it on there anyway. And let's go 300. Okay, well, what does that equal to? Well, exponentially, we would then go x 10 to the x is equal to 300. I wonder what that is. I wouldn't know because I don't know what power that is. That's when you can use your Desmos to come up with that. So you can go here and come down to here. Okay. So we want to get that log. So then if we come down and look under functions and miscellaneous, and there it is. Now there's 2 of them here. One is log. That means that's your common log, so it's a base 10. This one's log because it has a little a here. I call it log So that means you can take the log and put any base in there that you want. Well, ours is just common log. So we're just going to go log 300, and we get 2.47. So if I take 10 to the 2.47712, see how I'm getting close to 300? Okay, so that's it, all right? If you want to take the log of something different, say we have, and the base is not 10, then it's going to give you this, so let's put 5 there, and I'll just put 400 in here, okay? 3.77, which means if I take 5 to the 3.7227, see how close it's getting to 400, okay? It's almost there, all right? That's how you do that in Desmos, finding logs, okay? It's the best way to do it, all right? You can use a calculator if you want to, but Desmos works pretty well. Okay, so some of the things they're going to ask you to do is write, let me see, I'm going to get to them. change exponential to logarithm. So they're going to give you an exponential, kind of like what I was doing. So 3 to the 4th is 81. So that means we're going to change this to a log. So log, what's the base? 3. What are we going to take the log of? And that's going to equal what? There you go. That's all you got to do. Okay. Sometimes they'll put the number there. Sometimes they'll put a variable in there. Okay. If they put a variable in there, so they go a to the 4th is equal to 800. Not a big deal. What's the base? A. What are we going to take the log of? What's it going to equal? There you go. Okay. Not a big deal then. All right. So they'll have us go the other way. Change logarithm to exponential. I'm going to use 3 because I did it with 3 already. Okay, so now we're going to change this to an exponential. So what are we going to write? Right. Okay, so the base is 2. There's our base. Okay, we're taking the log of 64. These things got to switch. Okay, so the 6 becomes the input and the 64 becomes the output. All right, so all you're doing is rearranging it. Same thing happens again if they throw a variable in this one. Okay, nothing else, nothing much exciting, just same thing. So if they put a b here and they say this is 8, so then what are we going to write for our exponential? What's that going to look like? 5, yeah. To what power? 8 is equal to b. Okay. And that's it. That's all they're. That's with those. Okay. That's all they're going to ask us to do. All right. Then there's some deals where they find the exact value. Oh, graphing a log. Come on. I'm going to get rid of these guys here. Okay, so there's our log function. All right. Base is 10 because I just put log there. All right, remember, it's the inverse of an exponential. Okay, so the exponential hugs right along this line and scoots up. All right, this one hugs right along this line, goes up, but it's going up slowly. All right, so in this case here, guess I can't even get a point on there, so maybe I can zoom in a little bit, give you an idea. No, it won't do it. So here, it's getting very, very close to 0, but it doesn't touch it. Okay? So the domain of this would have to be what kind of numbers?
Positive x is greater than 0.
Right, x is greater than 0. It's never getting, not going to touch 0. In fact, it kind of gets right to there and it doesn't like it anymore. I guess I'm getting it to come down a little bit. But it gets real close to 0, but never touches it. All right. What about the range? Oh, real? That's okay. All right. So our basic log function, right? Domain greater or equal to or greater than 0, right? Not equal to, greater than 0. Range is all real numbers. That's good. All right. You can shift it around, do all the transformations that you want to it. All right. Obviously, they all make the same thing. So if we put a +2, it's going to shift it back. All right, we put a number out in front, that's going to be a stretch. Doesn't look like it, but it did. Stretches it. Put a negative in front, it's going to reflect it. Anything you want. Okay, nothing changes there. But that's your basic. Okay, that's what we called that parent function, I think, when we were doing transformations. Okay. Let's see. So I'll put that down here. Equals log of x. And if the base is different, it doesn't make any difference because you're just changing that power on the base. You're still going to get the same thing. So the domain, x is greater than 0. Range, all reals. That's what it looks like. So in case you're wondering, well, why is it that we can't take the log, say, of a negative number? Okay, why can't I do that? So let's look at this. Let's say this is 10. That's my base. To the y is equal to -3. So can I take 10 and raise it to some power and get a -3? Can we do that? Is there anything you can think of that you can take this number? Good. You get negative. It's 10. So that's why it doesn't work. Okay. Okay, before we take a break here, so last week I said we're talking about logs. So somebody said something about, well, do they have any interesting applications? I said, well, not really, because, sorry, they just don't. But, I mean, they use them years and years, I mean, a long time ago when they had slide rules and stuff like that, and they had to do calculations on huge numbers. They use logarithms because you can take the log of a big number and get it down to smaller. But then, calculators have taken and replaced all that, so we don't have to worry about that anymore. But they do have some applications on stuff, and let me see if I can pull this up, because it was kind of interesting. See if I can find the guy here that did this. I probably won't be able to find it now, of course. Well, we'll take a break now and I'll see if I can find it because it was kind of cool. I mean, what he did, it kind of was pretty neat. So we'll take a break now and I'm going to look for it, see if I can find it. That's going to be a logarithmic application. All right, decibels, pH, anything like that. All right, so if we have a pH, again, of 4, and then you measure it and it's 6 because you've added maybe some baking soda or something to it, that's only a change of 2, but it's actually 100 times more, or 10 to the second, and that's an application of a logarithm. All right, and that's where logs are used. All right, they don't have a lot of applications, but that's where they're used. So, a couple other things they're going to have you do. One, they're going to say find the exact value. All right, and they're going to give you this: log of 625 base 5. Okay, so what is that equal to? Well, obviously you could use decimals to do it, right? But they don't want you to. They want you to try to work it out without using a calculator or any type of technology. So I'm just going to put a little X there just for the heck of it. And we'll use the definition. See, here's where the definition is going to come into hand. So we're going to, here's my base. That's going to go up here. And now I have 625. Okay, so the output becomes the input. This is going to go right there. And now I just have to figure this out. Well, in the book, of course, they're going to make these really nice. Right? So all we got to do is figure out what that power is. Well, 5 to the second is 25. 3 is 125. 4 is 625. So the answer must be 4. All right? They're not going to give you one that is not going to work, because they want it to be an exact answer, and they don't want to use a calculator, otherwise we can't do it. So let's use decimals or something. So it's going to be 4. All right. And then they'll have another one. So we'll go log here. Let's do square root of 3 is equal to 9. All right. You go, what the heck is that? Well, that's okay. We can do this because we're going to use a definition. Right. All this is used in the definition. That's why I said if you can use a definition, you're all set. Did I do this wrong? No, I did it. This has got to go here. Equals. There we go. Okay, so now I'm going to use the definition. There's my base. Okay, x equals 9. All right. Okay, so my base here goes there. Output becomes input. And there's my 9s. So we got to get this square root of 3 so I can work with it a little bit. I notice that both of these have 9s, or 3, so I can write this as 3 to the second. Okay, so now I just got to figure out, well, what can I write that to? So a square root would be 3 to what power would that be? 1/2. Okay? So that would be like 1/2 x. Okay? 1/2 x. So now, just like the question Jessica asked, we don't worry about these. Okay? We don't care because they're the same base. They're the same number. So we're all right. All we got to do is focus on what's on the top part. So now I'm going to have 1/2 x equals 2. And then obviously x is going to be 4. And that's how you do that. But again, all you're doing is a definition. Okay? That's why the definition is so important when doing logarithms, because you use it all the time. Any questions on those? You want to see another one? Are we good there? Okay. Let's see. I'm just looking at these problems to see if there's anything here. Oh, I know what I wanted to do. Oh, I'm bouncing back and forth here a little bit. Hey, I need to mention this. So last week we talked about the number e. All right. And I said, well, I was going to come up with logarithms. So here we go. So the natural logarithm is just a log with a base of e. All right. Everything else is the same. It doesn't really matter here. We'll put x equals y. So that means we'd have e to the y is equal to x. All right? So the natural log is symbolized by a ln. So when you see ln, that just means that the base is e. All right, and nothing else. So that'd be e to y is equal to x. All right, ln is in Desmos too. If you look for it, it'd be there with the log functions. ln is there. You can use it. All right. Natural logs, well, you know, they're like logs. They have some applications. Again, not many, but they do have some. We will see those if you take more mathematics. You'll see some natural log stuff. So anytime you see a natural log, it's just a log with a base e. It has the same properties. There's nothing different. It's just that the base happens to be special. All right. So I wanted to do that with you. These, solving the equation here, right, they give us some problems. So let's do this. So we're going to go log of 3 to the 3x minus 2 is equal to 2. Okay? So we're going to solve this equation. We're going to figure out what x is. All right? Again, we're going to use a definition because that's the key. So here's my base. All right? Output becomes the input. That's going to go there. Now I write it. So see, I'm using a definition, getting rid of the logarithm, and writing it as something I can deal with. Now this is, heck, I can do this because all I got is 3 to the second there. And this is just a simple little solving equation deal here. All right? And we're good. So using that definition made that complicated looking problem pretty simple. Wasn't that bad. Worked out pretty well. And we can do that on any of these things here. So let's see if I can find one. We put the variable somewhere else. X of okay, so let's do this. So now we have, here's my base. We use a definition, x, input becomes the output, equals 16. So what does x got to be? 4. Yep. Okay. So again, all you're doing is just using a definition. It doesn't matter where the x is, you can use a definition to figure it out. All right, with logarithms. Okay. Any questions on that? Because that's all of 4.4. Oh, we're cruising here. Okay. 4.5. Properties of logarithms. So last week, I said, well, let's do some properties of exponents. We'll mention it because it's related to the properties of logarithms. So just a quick review of those. If we have a to the m times a to the n, that was a to the m plus n. All right? That was our first one. Since a logarithm is an inverse of an exponential, then we can write this in a log. So if we go log, okay, of a plus the log of b, that is equal to the log of a times b. All right. So notice that here, when we multiply two exponential terms, okay, we add the exponents. Here, when we multiply two terms inside a logarithm, we split it and we add those two logs. Okay, so they're related in that respect. Multiply, add. Multiply, add. All right, so let's go back. The second one looks like this. Said a to the m over a to the n equals a to the m minus n. So in a logarithm, oops, it's going to look like this. So if we're going to take the log of, I should have probably wrote that the other way, a over b, that's equal to the log of a minus the log of b. All right? So when we're dividing two exponential expressions, we subtract the exponents. So when we divide something in a logarithm, we're going to subtract the logs. That's how that works out. Same thing, very, very similar to the properties of exponents. One last one. This one's not quite as clear to see. So if we have a to the m to the n, then that was a to the m times n. But properties of logarithms, if we have log of a to, say, the m power, then what happens is that this number flies out in front and it becomes that. Okay? So if you're taking something to a power in a logarithm, then that power comes out in front automatically. All right? So there's your properties of logarithms. And they mention those on one of these pages here. .326. That's where they are. Now, they have a lot more properties of logarithms, but really they kind of make sense, but I'll mention them just for the heck of it here. All right. They have one that looks like this, and it can be related to exponents. They have the log of m base a. So a, these two things have got to be the same. When you have a log a to the m as an exponent, okay, and this base and this base are the same, then all you're going to get is an m there. All right, so if we had, say, 2 to the log, and the base is 2, and this number was 10, then the whole answer would be 10. Okay, so basically what's happening is these 2's are just kind of canceling out. All right. But I think, see here, we had this, and we said that was equal to an x. Then we'd have a to the x. And I guess I couldn't be. Well, kind of could be. Using the definition of a logarithm. No, it wouldn't work out very well. Okay. So there's that one. What other one did they show you here? They talk about the change of base formula, but the change of base formula has pretty much been eliminated because you don't really need it. It goes like this. So it says the log of m base a is equal to the log of m over the log of a, where you can choose your base. So back before all this technology was around, and you had the log of, say, 205, and the base was 5, there was no way really to figuring that out. So then you used the change of base. It was pretty helpful. And you could switch it to whatever base you wanted. And you would always choose base 10 because you could use your calculator to figure that out. Okay, but now things have, have come out so much. You use Desmos or whatever calculator. You don't have to worry about it. You can figure it out straightforward. Okay, so you really don't need the change of base, but they mentioned it. Okay. So I think that's all the properties of logarithms that they really mentioned in here. Okay. So now it's just a matter of working through these and figuring out how do I get the answers. Okay. So like for example, it says use props of logarithms. To find exact values. So here we go again. So we'll go to log of 2 base 5 plus the log of 9 base 5. No, we better, I'm sorry, I don't want to do that one. Because we need an exact value. Let's get rid of the 5. That's not going to work out too well. Make this a base. So something like this. So then what you would do is first write this as use your properties of logarithms and write it as a log base 2 of 2 times 16, which equals the log base 2 of 32. Okay, so we're going to use the properties of logarithms. So then when we add, we multiply. So we're going to multiply these two things right here. Okay. Keep the base the same, nothing changes there. Okay, I'm going to put a little x there. So now I'm just going to go 2 to the x is equal to 32. Again, these are always going to work out because they're in the book and they're supposed to work out. So 2 to the x equals 32. I'll just count. So 2, 4, 8, 16, 32. So x has got to be 5. All right. Okay, and there's the exact answer. The other one wouldn't have worked out because it was a base of 5 and 5 wouldn't have worked. Okay. So we're using the properties of logarithms there and the definition. So you're still using the definition. So here's 1. 8 of 16 minus log 8, 2. Okay, so we're going to use our properties of logarithms to get down to a single log. What would that look like? Log what? Log of 8, and what's the base? Base has got to be the same as these. So what's our base? 8. So since it's a minus, we're going to take 16 and divide it by 2. That's where that 8 comes from. Okay? This is a simple one because we just have the log of 8 base 8. 8 to some power is going to be equal to 8. Obviously, that's 1. Okay? So, again, we're using our properties of logarithms. All right? Up there we had a plus, so that was a times. Here we have a minus, so that's a division. So we just take these two things, divide them. The base stays the same. And then you just got to work it out. Using the definition. Always using the definition. they'll have you do this, right? Each expression as a sum or difference of logs. Okay, so you're going to use your properties of logarithms again. All right, so they're going to give us something like this. So they're going to say, hey, let's do this. So we have the log of 4a to the third. Okay, so we look at our properties of logarithms. All right, see what the heck's going on there. So I see that in my properties of logs. Where are they? Way in the heck up here. When I have a log with a power, like this m right here, okay, it pops out in front. So then I take that problem that I have, go down here and find it. There it is. I'm going to take this 3. It's going to pop out in front. Everything else stays the same. I don't have to do anything more. I just leave it like that. Okay, 3 pops out in front. That's all we're doing. It's using your properties of logarithms. Log base 5 of x over 10.
Is that a like an exponent, or is it just like?
It's what you take in the log. So this a or this a? This one? It's what you're taking the log of. So, you know,
So it's not like a power.
no. No. So this is your base. So this is a subscript, right? And this is what you're taking. So here, we've got the log base 5 of x over 10. So, x over 10. So then I go back up here, okay, find my properties of logarithms. There they are. I notice then that I have a minus b is a over b. Okay, so come down here. That's what I'm going to use. Log of x, base 5, base doesn't change, it's division, so I'm going to subtract log 10. That's all I got to do, okay? I'm just rewriting these things. Just rewriting them. Okay, let's check this one out. All right, so here's one that tricks people up. So we have a log, okay, base is 10, log of 3 squared x. All right, so this is 2 things that's happening. One, we have a multiplication going on there. So I know then I'm going to have this plus this. Okay, because I got multiplication. But I'm not done here because this is a 3 to the square, so that means I can put the 2 out in front like this. Now it's done. Okay? Now it's done. That 2 is going to pop out in front because that's my properties of logarithms. So we have 3 of them. Okay? Division, multiplication, and that power. And that's it. Questions on any of those ones that we did? Rewriting these, using those properties. I feel like I'm going kind of fast, so slow me down if I need to go slower. Okay, they're going to ask you to go in the opposite direction. All right, so they're going to say, write as a single logarithm. So now we're going to have something that looks like this. So we'll have log of 4 minus the log of u. All right? So now we're going to go the other direction. So we got to figure out, okay, which property is this and what does this mean? So when I have a minus, what are we going to do with these two things? What are we going to do with the 4 and the u?
4 over u.
Yeah, it'd be 4 over u. When we have a minus, it's division. When we have division, it's a minus. That's it. That's all we got to do. You can't do anything more. You're just writing it as a single logarithm. Three log v plus log 8. Okay, now we have one like this. Plus means what are we going to do with the two things in the logarithm? Multiplying. But we have this, okay? So we have to be conscious of that. So we're going to have 3, okay, log v8. But this 3 has got to go up here where the v is and become an exponent. So it really looks like this. Mathematically, of course, we'd write that as 8v cubed. Okay, because this 3 is in front of the v, it goes to that. All right. Now, if it's written this way, parentheses, parentheses, then that's different. Okay, you're still going to multiply the 8 and the v. It's just that now both things are squared. Okay, because that 2 is outside a set of parentheses, that means that both of these things are getting squared. Whereas here, only the v was getting powered. All right, so there's a difference there. Well, that really is pretty much all there is to these. Okay. But it's a lot of stuff on logs because you have the definition and we have all these properties. Okay. So there's a lot of things there. All right, let's try some out. Give you some time here to work on some.